We have focused so far on situations where we have one variable that we observe over time, and we want to try to model or estimate this particular variable value through using only past observations. But there are settings at times where, in addition to this variable of interest, you might have access to some additional information that could be used to help explain the variation in your main variable of interest, like through using a regression model. And so in this particular setting, we're going to use regression models like you've seen elsewhere, but now we're going to get away from the typical error term assumption of independent mean zero variance sigma squared. And now we're going to introduce allowing dependence amongst your error terms. So this setting then is called regression with ARMA errors. So to help set this up, let's just do a really brief review of what you would see with regular old regression. Here's our model. We have a response variable y. We have explanatory variables x through x1 through xr. We have regression parameters beta 0, beta 1 down to beta sub r. We have an error term epsilon sub I, which is just again distributed independent normal 0 sigma squared. Notice how I have an I on each of these y's and these x's and the epsilons corresponding to our sample, I equal 1 through n. So we take a sample size of n. And we can put all this stuff into a matrix form, such as y is equal to x times beta plus epsilon. So y is a vector of all of our y variables. X is what's often referred to as a design matrix, where we have a leading column of ones, and we have the corresponding variable values for x1 through xr written in it. We have our parameter vector, or regression parameter vector, beta 0 through beta sub r. We have our epsilon vector as well, epsilon 1 through epsilon n. We can say that this epsilon is distributed multivariate normal with a mean vector of 0, a covariance matrix of sigma that has a specific form. Simply, sigma is equal to sigma squared I, where I is the identity matrix. Now, in this matrix formulation, of course, when we take x times beta, what's happening here? We're taking this row times this vector, then we take this row times this vector again, and so on. And the least squares estimate for beta, we denote it as beta hat. This is a vector, and it's x prime x inverse, x prime y. This all should not be new to you coming into this course. Now, how are we going to change things once we allow for dependence amongst our error terms? So in other words, instead of having zeros here in the off-diagonal elements, we will have potentially non-zero values. So this is what our model is going to look like. In terms of our notation, we have our response variable y sub t. We again have these regression parameters beta 0 through beta sub r. Now our explanatory variables, or independent variables that we're going to have with our model, are going to be denoted as z sub 1 through z sub r. And then my error term, or what normally we would have as an error term, is going to be denoted as x sub t. This corresponds to how we've been using x sub t in this course so far when we've been trying to model our response x sub t. So note that this x isn't like an independent variable or explanatory variable like you would see normally in regression analysis. Rather, this is going to take the place of our usual error term in regression. Also notice that our subscripts, we don't have a subscript I on these quantities. Instead, we have a subscript t because we're going to be observing these values over time. So y1 would be the response variable observed at time 1. Z sub t1 would be an explanatory variable, the first explanatory variable that's observed at at time 1 as well. So z sub 1, I should have said that. We can put everything into a nice vector form. So we have beta prime times z sub t plus x sub t. We could put everything into a matrix form as well, using just the usual form. Now notice this x here is a n by 1 vector. It's distributed normal. We're going to need to assume normality again to get these parameter estimates, with a mean vector 0 and a covariance matrix of lambda. Now this lambda has this particular form here. So at comparing time 1 to time 1, we have gamma sub 1, 1. That's our usual autocovariance that we would normally see for comparing time 1 to time 1. If we can assume stationarity, then we would call this gamma of 0 itself, because there's a 0 lag difference. Gamma of 1, 2 is the autocovariance function for time 1 versus time 2. Again, if we can assume stationarity, this just becomes simply a gamma 1. And so this is our form. And the key difference then is that notice that these autocovariances could be not equal to 0 in comparison to regular old regression analysis. So you might be wondering, okay, well, what do we put in for these elements of gamma? Well, it all depends upon your ARMA representation for x sub t. And we've obviously have seen ARMA representations for x sub t, just in a context of where x sub t was our only variable of interest in the past. But that same structure for the autocovariances now can be applied here for the structure for the covariance matrix. So for example, let's say that x sub t has an AR1 structure to it. So what that means then is that we can think of our error terms in our regression model, x sub t, as coming about as follows. A phi1 times your previous times error term, plus now a wt, which is independent with mean 0, variance sigma squared. We could, of course, then write this x sub t out then as an infinite order moving average like model 2. So then what our model now becomes then in this kind of a setting is that we have y sub t here. We have beta prime times z sub t to account for our explanatory variables, independent variables that are observed at time t, plus now this extra component here. Now with regular old regression model, we would just have an epsilon there, one epsilon, which would be, and each of them would be independent. Now look what happens though. Now we have a linear combination of what will be equivalent to our epsilons. This w here, because that's white noise. They're all weighted, and we go back in time to get these w's. So in this particular case then, what would our covariance matrix look like then for x sub t? Well, we've found previously the variance of x sub t, the variance of x, the covariance for x sub t for a lag h difference. So using what we've done before then, we can write out our our covariance matrix then as this. So notice that each of these, the variances and the covariances, have a common component to it, that sigma squared w over 1 minus phi1 squared. So I have that there. And then if I have a covariance, meaning that I would have an off-diagonal element of this matrix, I have phi1 raised to the h power. So for example, this phi1 means I have this is the excuse me, the covariance between x1 and x2. So now that I would have a phi1 there times the rest. Here is the covariance for x1 and x3. So now I have phi1 squared, and so on. The diagonal elements are all 1 because notice what that variance is. It's what we already have out in front. Now, many of you have probably also seen this kind of a structure before for a covariance matrix, especially when you're working with generalized linear mixed models where you have to worry about dependence that might occur over a short period of time amongst your observations. And you would have often referred to this as an AR1 structure. Well, this is where that AR1 structure comes from. So for other ARMA models, you do exactly the same thing. Use what we've learned before, put it into a covariance matrix like that. Now, how do we do the estimation? Well, simply maximum likelihood estimation. Again, you have betas to worry about, sigma squared W, you have phis to worry about, and also thetas to worry about as well. If you're interested in learning more about the details, here's one particular reference there. Also, very often towards the end of books that are used for a full course on regression analysis, you typically will have a section on regression models with non-independent error terms, and that would also talk about how to go through the nitty-gritty details of estimation. Okay, so let's take a look at an example where we can apply these methods. This example comes from Shumwayne Stouffer's book. It deals with pollution in Los Angeles. And what the authors are interested in doing is using explanatory variables or independent variables of temperature, temperature squared, and the particulates that are in the air as a way to estimate cardiovascular mortality over time in Los Angeles County. And what we have here are weekly observations for 10 years. Now, the authors do not provide as much information about this data as I wish they would. So they don't say, well, how do I get this y sub t for cardiovascular mortality? And what it appears to me is that this is simply representing the number of deaths per week out of a total number of individuals in terms of a scale. So for example, you might see 93.84 deaths per 100,000 people that are attributed to cardiovascular mortality. That's what I'm talking about here. Maybe it's a per 1 million scale. It doesn't, the details are not there. But I bring this up because how do you get a 0.84 of a death or 0.5 of a death? So that's why I think it's put on a numerical scale like that. Also, the numerical scale for the number of particulates is not given too. I think it's just safe to say the larger the number is, the worse it is in terms of air pollution. Okay, so this data is in Shumwayne Stouffer's corresponding package, ASTSA. And what I'm going to do is create a data frame called MTP. And this is going to contain the vectors that the authors have put together for this corresponding data. CMORT stands for cardiovascular mortality. Temp R is that temperature. Part is the particulates. And also I'm going to form a variable called T, which just simply gives me 1 to the number of observations that are in the data set. I think in total there might be about 600 observations. So this is what it looks like. So at time 1, these are the particular values that were observed. Next, I'm going to plot my data much in the same way as we've plotted the data before. I'm going to plot both, I'm going to plot cardiovascular mortality, temperature, and particulates, because each of these are being observed over time. And this is what we get. Let me make this a little bit bigger. And so what we can see here is that we do have appear to be trends over time here. Here's our y sub t, which we will use symbolically to represent cardiovascular mortality. And we definitely see some trends that are occurring. Obviously temperature, there should be trends amongst temperature, and that's what we have here. We'll call that capital T sub little t. And similarly for particulate data, we'll call the particulates capital P sub t as well. So, it makes you think, okay, well, we have some trends over time. how can then we model cardiovascular mortality? How can we take advantage of these trends? Okay. So I'm going to focus on the particular final model, essentially that the authors chose to model this data with. And so, I don't know why I switched notation here, I apologize. We're going to let capital M sub t be cardiovascular mortality rather than Y sub t. Here are my corresponding regression parameters. I'm going to use this little t, which represents time. So we had a column in our data set representing time, 1 through, actually it's 508. Very often with these kinds of regression models, it's good to include this kind of a variable in it because, again, we're expecting to see trends over time, and this t helps to account for that. Here's my temperature. And then the authors say a temperature squared is needed. So there's my temperature squared, the particulates, and then here's my, what we normally would think of as an error term, my x sub t. So I have x of t is the error term. That shouldn't be there, assumed independent for each t. Excuse me about that. Now, at least initially what we're going to do is that we're going to look at what if I did assume independence for each t. And so what we're going to do is estimate a regular old regression model and see where that takes us. So I'm going to use the LM function to actually estimate the model. Formula that tells R what the corresponding model is. Here's my dependent variable C mort. Tilde, there's the T, the temperature, plus a temperature squared, plus particulates. There's my data frame MTP. Now, depending upon if you've used regression, if you've used R for regression, you may not be familiar with how I get temperature squared in the model. So, to represent a squared term in a formula argument, you need to enclose it inside the I function, which stands for identity. Here's why. Let's say instead I had some variable we'll just call a, and I wanted to have a squared in the model. If I were to only include it as a caret 2, that has a different meaning to R than what we would think in terms of wanting a squared. To help see that better, suppose I have two variables, a plus b caret sign 2. If I were to put that in a formula argument in R, what this is going to correspond to is this. You would have a, you would have b in the model, and you would have a times b, the corresponding interaction. So what the caret sign and then a corresponding number associated with it represents is that basically you want as high or as whatever that number is in terms of the order of the interaction. This is a second order interaction here. That's what the caret sign with a number next to it actually represents. You want all the previous terms up to that high of order for an interaction. To have R actually interpret this correctly in terms of we want a squared, that's where the I function comes in. Okay, so I put the results into mod.fit.lm. And then I summarize the results as well, and this is what I get. So for example, here is beta hat 0 right there. And let's take a look at the residuals. So one component of the return list that LM produces is the residuals. I can pull it out of my list using $residuals, much as we've done with the ARMA function. And this is what I get for the plot of the residuals over time. And it appears that we are having some trend that remains in the residuals. And if we have trend, that says that the corresponding error terms are not independent, which violates assumptions for our corresponding model. If it violates assumptions for our corresponding model, that means our inferences that we could be making to the population could be incorrect, because now this model is not correct to use in this situation. We can take a look at ACF and PACF of the corresponding residuals and look what we get here. we have some significant values at the lower lags. In particular, the PACF, we have two large values, one at lag 1 and one at lag 2. And then over here in our autocorrelation function plot, we have some large ones too. And if you maybe ignore what's happening there, you can see maybe we're having a tailing off pattern, similar to what we've seen before. Okay, so some notes. I could go ahead and write out my estimated model based upon what's given in the output. So for example, here's that beta hat 0 that I pointed out before. Since this is an estimated model, the convention is to actually write out m hat sub t with that particular model. We've talked about the identity function. These residuals, we had two significant ones for the PACF. Maybe we have a tailing off to 0 for the ACF. That pattern that we see there corresponds to what we've seen before for an autoregressive 2 model. So what we're going to do shortly is now say, what if we have this x of t being an AR2 model, and see what happens. And we've also talked about this last bullet too. Okay, so how can we estimate the model now where we have everything that we had before, but now x of t has an AR2? There's a few different ways to actually estimate these models in ARM. I'm going to focus on the way that would be, let's say, most familiar to you based upon what we've done previously in the course. And I'm going to use the ARMA function with that xreg argument that we've seen briefly in the past. So to estimate the model, I'm going to put my results into mod.fit.arima1. I'm going to use the ARMA function. Here's my response variable, cmort. Now, and let me back up a second here. Let's actually first estimate this same model, assuming independence, but now using the ARMA so you get used to the syntax that's used here. Then we will estimate the model with the AR2 component. Sorry that I didn't say that's correct at first. So now to estimate the model under independence, then for my order argument, well, I have a 0, 0, 0 for P, D, Q. Then for the xreg argument, what I need to do is put in my corresponding explanatory variables that we have. So here's my T, here's my temperature squared, and the corresponding particulates. I could have pulled this information out of my data frame that I had previously done before. That would have been just fine. For some reason, in the end, I just only chose to pull T out because that was the only thing that was new. Otherwise, I just work with the original vectors themselves. Okay. So let's take a look at that corresponding model. And so what we have here, look at this. There's beta hat 0. Here's beta hat 1, and so on. Here's my sigma hat squared W as well. And if I were to do a plot of the corresponding residuals then, do note that since I did use them the original vectors here, these are actually of a class of TS, and that causes a little bit of problems with how the residuals are actually outputted to us. And in order for the residuals to be represented well on the plot, I need to actually include TS here in terms of make this a TS class for these residuals. And so that's just simply what I have to do the plot. Otherwise, try it yourself without it, and you're going to see the plot's a little bit distorted in terms of where the autocorrelations are actually plotted. And so this is what we get, exactly the same as what we had previously when we used the LM function. So the purpose here is to draw the connection between using the ARMA function to estimate a model under independence versus using the LM function, which is what we would normally use to estimate a model under independence. Note also here, in order to put together these values for the xreg argument, I needed to use the cbind function. Cbind stands for column combined together. And so on your own, you could actually execute this segment of code here and see that everything is just put together into what actually R would call a matrix form. Okay. Now, one of the strengths to using the ARMA function to estimate this model versus using some other functions that are available in R to estimate this kind of a model is that now we can go back to using my examine.mod function that we've used previously to examine various diagnostics corresponding to the model's fit. And so what I can do is source in the examine.mod.r file, or just simply open up this corresponding program in my programming editor and just simply run that entire file. And so when I say examine.mod, for my model fit object, I put mod.fit.arima1. I give it a name so I can identify it with the corresponding plots. And let's say here I use a max lag of 20. And this is what we get here. We have the usual z-test statistics. We have the usual p-values associated with it. Since I'm assuming independence, I shouldn't actually look at any of the p-values though, because inferences will not be correct, because the model assumptions are violated. And let me make this a little bit bigger here. So I get my usual standardized residual plot. Notice how this goes up to 4 there. Notice also how it seems like we have blocks of residuals that all have the same sign as well, indicating that yes, looks like there's the residuals are dependent on one another. We get the same ACF plot of the residuals as we saw before. Unfortunately here, R uses a weird lag notation here, or numbers. This just simply comes about since we had weekly data. This 0.1 here represents that we have 10% of a week. 0.2 represent we have 10% of a week, and so on. The actual lags are correct on the p-values plot for the John Box-Pierce statistic test. And we can see we have significant autocorrelation. Here's the PACF plot we've seen before. Histogram of the residuals. Looks like we have some right skewness. And that's actually shown in this QQ plot as well. Okay. Let me make this 100% again. Now let's go ahead and actually estimate this model using an AR2 model for the corresponding error terms. Let's see what we get. Okay, so again I say ARIMA, and also I'm going to put the results into mod.fit.arima2. My order of my model when I am modeling CMORT is P is equal to 2, D is equal to 0, Q is equal to 0. I'm going to combine together my T, my temperature squared, and particulates as well. Here are the corresponding parameters estimated from the model. So here's phi hat 1, phi hat 2, beta hat 0, and you can see some of the other beta hats there, along with the corresponding standard errors that take into account now that we do have the non-independence of our error terms. We can examine the model's fit more closely using examine.mod. So notice this is mod.fit.arima2. My model name is regression with AR2 error. This is what we get. Now it's okay to take a look at these corresponding p-values. Well, as long as all the model assumptions are satisfied, and I will tell you through our diagnostics we will find that they are. For this particular model, it's okay now to look at these p-values, and we can see that we have very small p-values indicating that there's sufficient evidence to indicate the corresponding parameters do not equal 0. Let's zoom in on this plot here. And here are my standardized residuals. This plot looks a lot better than what we saw for the previous plot. We don't have a large sequence of values that are all positive or all negative. Notice now we have +3, we have -3 as essentially the outer bounds, and again we have about 500 of these residuals. So it's to be expected that we're going to have some that are outside of ±2, but not a whole lot that are outside of ±3. And so this looks good. In terms of my ACF plot of the residuals, of course, we don't look at lag 0 there, but notice all the values are within our normal bounds of ±1.96 divided by the square root of n. Here's the p-values for the Jung-Box-Pierce test. We have all large ones, starting to get a little bit small here, but otherwise they're all large. PACF plot as well, that's looking good. My histogram of the residuals, hey, this is actually looking better than the previous one. It looks more like a normal distribution. QQ plot as well is also better than what we've had in the past. Okay, so I've estimated the model. This model looks good. Now I need to actually state the model. And so you need to actually go ahead and formally do this. So here's my model. My estimated mortality at time t, or in other words, m hat sub t, is equal to beta hat 0 minus beta hat 1 times t, and so on. And then it's important as well to state then that corresponding AR2 component now of our model. So I just state the AR1 part just like what we do normally. Okay, so and we've talked about the other notes there as well. Now I purposely estimated the model with the AR2 model to try to duplicate what the authors did in their book. And yes, we've duplicated what they've done. But let's say, though, we didn't know what kind of model to use at the very beginning. What could we do? Well, suppose rather than starting with an AR2, suppose we start with an AR1. We look at the model, and then we look at the residuals, and let the residuals guide us to let us know if we need to make some changes to the model. So let's do that. I'm going to put my corresponding model fit into mod.fit.arima3. Here's the ARMA function, my response variable. P is now equal to 1. Xreg, I put together my corresponding explanatory variables. So this is what we get. Here's phi hat 1. Here's beta hat 0. I use examine.mod to examine the model's fit a little bit better. Notice if we're comfortable with that, if the model did actually fit well, we could look at these p-values and interpret them. But it's best to hold off on that until we take a look at the corresponding diagnostics for our model. And this is what we get. So the standardized residuals here, similar to what we've seen previously. I don't know, maybe there's some patterns here, but it's really hard to see. I mean, it looks like almost we're having alternating positive and negative values at the time. But really, look for large trends here, similar to what we saw when we had all independent error terms. Focus, though, on the ACF plot of the residuals. We have a significant value here, 1 here, and of course we don't look at lag 0. P-values for the Jung-Box-Pierce test. Ooh, those do not look good at all. They're all small, indicating that we do have sufficient evidence to indicate that there is some correlation that's amongst our residuals. This violates one of our assumptions of our corresponding model, because once we take into account, in this case an AR1, we would expect now what our W's to produce is all independent. Okay, so it looks like we got some problems. PACF plot also indicates that we have problems. Here's the histogram of the residuals, normal QQ plot, not too bad. Now, we should be able to take a look at these residuals, and that should guide us then to how we can make changes to our model so that our corresponding model is satisfactory. And so I don't think this, in this particular case, necessarily leads us to adding one additional AR term to our model. We have two values here, so one thing that I might want to do is, well, let's start with adding one AR term. If that doesn't work, let's look at another AR term, and so on. Now, if it was purely an AR aspect, we would expect that this ACF plot of the residuals is tailing off to 0. Is it? It's really hard to say. In fact, you might say, well, maybe I should add an MA1 term or MA2 term as well. And so what one typically does in these kinds of situations is that you look at a variety of different models and see if that helps you. And so, for example, how about we look at an ARMA 3.0, since we've already done ARMA 2.0. So I'm going to put the results into mod.fit.arima4. Here is my P. And actually, for some reason, I didn't actually put the corresponding code there to actually estimate the model, but you can see the code right here. And so this is what we get. Now notice here is phi hat 3. Look at the corresponding estimated, or the square root of the estimated variance for phi hat 3. Well, if I were to take the ratio of these two things, we would know that that ratio would be between 0 and 1. Therefore, the p-value will be large. There is not sufficient evidence then to indicate that indeed that the phi3 term, phi3 parameter is actually significantly different from 0. In fact, actually, I do have the p-value right there. It's 0.4. One can look at some other diagnostic plots as well. Let me zoom in. Standardized residuals look good. ACF plot of the residuals looks good. P-values for the Jung-Box-Pierce test look good. Everything else is looking good, but it's kind of hard to justify leaving in a parameter in the model when the p-value is 0.4, and when we know that the AR2 model seems to fit the data rather well. Okay. So then I guess just in summary, not just for this example, but for other examples, well, how would you go about then, let's say, the model building process when you're faced with a situation like this? Well, here's my recommended approach. Simply fit a regression model with independent error terms, like what we did. Estimate the ACF and PACF plots, examine the ACF and PACF plot of the residuals to determine an appropriate ARMA model for those corresponding error terms. Estimate that regression model now with these new way of looking at these error terms, and then look at the ACF and PACF plot of the new model's residuals, and let those residuals help guide you to a direction of how to handle these error terms here. And again, you might have to do this in an iterative manner. Okay. So one of the main purposes then of time series analysis is to be able to forecast the future. Well, how does one do that in this particular situation? Well, there's a problem. In order to forecast future values for, let's say, like m sub t, we need to know what future temperature values are going to be. We need to know what the future particulate matter value should be at one time point in the future, 2 time points in the future. You need to know all that in order to forecast future values for cardiovascular mortality, because now you've set up your regression model to be dependent upon this extra information. So then the question is, well, what do you use for these other unknown values? And there's not necessarily a good solution for that within this kind of a regression setting. As you will see in the example, I chose, well, why don't we just use values that are similar to the ones that we just observed if we're only going to have, let's say, 1 time point ahead or 2 time points ahead. But otherwise, you're simply guessing what would be particular future values to use in this particular model. So then, in general then, well, how would you actually come up with then the forecasted values? Well, let's say we're interested in y sub t plus 1. Well, you would take your model. Let's say we're just working with the true values for now. So you take your model, and then you have your you have your beta vector, your regression model, your vector of regression parameters. Transpose that times then these future values of z, which again you might have to guess. And then now look at that sort of error term there. Now you put in there that forecasted value given your past time points. And so you could actually write this better. Maybe instead of using t, use n to say, I've already observed n information up to n. What's the next time point value? And so you could replace the t by n there. Well, what about the variance then for the predicted value, or then the forecasted value? You know, because you want to have like a 95% confidence interval. What do you use for that variance? Well, in a regression, in your previous regression experience, you've looked at how to find confidence intervals for then the corresponding response. Basically, do the same thing there, but instead of only using z prime sigma hat times z, which you would normally use under independence, you will end up having a little bit extra component there corresponding to the variance from the ARMA model. I'm not going to go through the details. Don't worry about those details. But essentially, that's what you would have. Okay, and that will allow you to come up with confidence intervals for y sub t plus 1 or y sub n plus 1. Okay, so let's go back to this Los Angeles pollution example again. And what I want to do is go one time point into the future to estimate cardiovascular mortality. And so what I have here for my data set, I have the last 6 observations in my data set. So for example, right here is M sub 508. And then to do the forecasting, I can use the predict function, like you would do with like as we've seen before. Object equal, here's where my model fit is. I'm using that AR2 model for the corresponding error terms. N dot ahead, how many time points do I want to go ahead? Just one. SE.fit equal true, so I get my standard errors. And then I have a new argument here, new xreg. And this is where I put together what these future values would be. So, and you have to be very careful about this. You have to do it in the order that you use in the ARMA function when you specify the xreg argument. So the first element always was t when I used the ARMA function. And so now, since I want to go one time point ahead, I have to change myself, t to be 508 plus 1. Then I put in my temperature. And like I said, I'm just going to use the previous temperature because I don't know what that temperature would be otherwise. If somehow you knew the temperature would be different, well then put in that value. Here's my temperature squared. And then here's the particulates from the previous time point as well. I put all the results here into an object called for.mod. This is what I get here. So y hat for 509 would be 87.104. Here's the corresponding standard error. So in other words, the variance of y hat t square rooted. Okay. To find my corresponding confidence intervals, I take that forecasted value, subtract off the value for my standard normal, times that standard error. That gives me my lower bound. Do a similar thing for my upper bound, but I put a plus there instead. And this is what I get then for the corresponding confidence interval. So this would be for 509, 97.1 is the upper bound, 77.1 is the lower bound. Okay. So some additional comments to conclude here. Basically, the estimation procedure that we followed here is very similar to something that was developed long ago by Cochrane and Orcutt. So you will still see people referred to as a Cochrane and Orcutt procedure. In fact, there is actually one function, at least in R, that implements it exactly as these individuals did when they developed it in the 1940s or 1950s. Basically, the standard way to handle this now is very similar. It's not exactly the same, but it's very similar, but it's what we had indicated with the maximum likelihood estimation approach. Again, there's other functions out there that will implement the model fitting. Another one that will do maximum likelihood estimation is the Gls function of the NLME package. This is actually the function that I've used many times previously when I've taught this course. When I most recently updated my notes for when I'm teaching this course, I decided to not focus on that particular function and use the ARMA function instead. And there's pluses and minuses to using either of them. I simply chose to use the ARMA function because it's uses a similar framework to what we've been using for other models in the course already. But real briefly, I think it's just worthwhile to show you what this other function looks like, what it can do, and so on. So I need to indicate that I'm going to use the NLME package, which stands for Nonlinear Mixed Effects. GLS stands for Generalized Least Squares. I'm going to put the results from estimating this model into mod.fit, and this is with the LA pollution data. This code is actually in my corresponding program. Then, instead of a formula argument, I have a model argument to specify the formula for the corresponding model, and I use same syntax otherwise for that. My data is an MTP, and then this is how I can specify then the error structure for the the correlation structure for the corresponding error terms. I have an argument called correlation, and I want to use an ARMA model. The form for that model to say, well, what essentially is time, I need to say tilde t. Remember, t is inside of my MTP data frame. And then to say, well, what kind of ARMA model do I want to use? I want p to be equal to 2 because I'm doing an AR2. Put the results into mod.fit. Then I can summarize the fit using the summary function. And this is what we get. So for example, here's phi hat 1, here's phi hat 2, and again, here's beta hat 0. These parameter estimates are very, very, very similar to what we get with the ARMA function as well. Do note that the model fitting process does seem to take longer than the ARMA function. And so like when I run this code here, my model fitting results do not immediately return to my screen or in the R console window. Okay, so if you take a look at the Shumwayne-Stouffer example about how they approach it, it's basically the same way that I did, at least with the AR2 part. They don't look into other aspects really. They, instead of using, let's say, temperature directly or particulate matter directly, they mean adjust the explanatory variable. So they have an explanatory variable that's the temperature minus its mean, which they call T dot. This simply just represents maybe an older form of how people often approach these kinds of models when there was like a square term in the model. In the end, it's not going to change things in terms of what your final answers will be once you take into account that that you're using your mean adjusting. I don't think it's needed here, but I just wanted to point it out to you if you read the corresponding example in the book. Now, there are other ways to handle having this additional information to help explain to help explain the variability that's in your main variable of interest, like cardiovascular mortality. There are what are called transfer function models. Sometimes when I teach this course, I also teach that section too. So stay tuned for that if I do that additional section. So that then concludes how to work with these regression models when one has ARMA error terms, and that's it.